Engineering is glad to introduce the honorable speaker for today's forenoon session, Mrs. Manju Annie Woman. Mrs. Manju Annie Woman is currently working as Head Integrated Systems Global Product Marketing in Fujitsu. She is a quantum computing enthusiast and spokesperson. She had completed BTech from College of Engineering, Trivandrum, in the year 2005 and MBA from Indian Institute of Management and Technology. She has extensive experience working on key technology partner software for converged and hyper-converged infrastructure architecture, leveraging artificial intelligence and quantum-inspired technology solutions to deliver data-driven business values. She has over 12 years of experience in the IT industry in Hewlett Packard Enterprise. Her research interests include artificial intelligence, high performance computing, hyper converged infrastructure, SAP infrastructure solution, and in memory computer requirements. This is a very brief introduction of our erudite and distinguished speaker. Before I conclude, I thank the college management, HOD, Department of Mechanical Engineering, organizers of the FDP, and each one of you for providing me this opportunity. Thank you, one and all. Now I request our honorable speaker to take over the session. Madam, you can just carry it.
Thank you. Thank you so much for the introduction as well.
Thank you. Thank you.
And really appreciate having this opportunity to discuss with all of you. And I would also appreciate questions. Yeah, this can be an interactive session, so please raise any questions that you may have. One more thing is that I do not know at what depth or what level of understanding that you have. Yeah, so in case you feel some of these are basic things, so you can stop me and tell me that, let's just proceed. Yeah, so that it would be useful for you. Okay, so my intent is briefly touch upon why are we actually even considering quantum computing. Yeah, so because quantum phenomena and quantum mechanics has been investigated since, let's say, late 18th century and early 19th century, and it has been in one of the research. It has always been one of the very favorite research topics for every scientist across the world. But now, in the past 2 3 years, it has gained a lot of traction with quantum computing. Because there has been some vendors, I mean, IT companies in the market who've been able to leverage some of this quantum phenomena into computing technology to leverage the capabilities of quantum. So we'll see what it is and how it actually impacts from a use case perspective, or how is it going to be useful for us, and why are we actually considering utilizing this phenomena into the computing architecture. So I'll also take you through what progress we have been making generally across different IT companies, and what kind of quantum computing systems exist in the market today, and some of the use case and real world scenarios it is used to solve, and at what scale is it being used to solve. Okay, there is also a concept of quantum inspired computing. That's precisely what I actually, from my background, that's what I work on, and in the company that I work with in Fujitsu. And we'll just look at what exactly that is, and how is it helping in some of these use cases defined in quantum computing. Okay, so let's just get started. So as I mentioned, classical computing, that as we know through the semiconductor chips, has done extensively well. Yeah, it has empowered the world. We've seen the phase of internet. We have Internet of Things, ensuring that there is integration between all sensor devices or edge devices across the world. These things are something which happens today based on the classical computing architecture. Yeah, but the classical computing architecture has extensively progressed over a period of 50 years to include roughly 10 10 billion or 10 trillion, sorry, 10 trillion transistor counts. And transistor counts are what gives the power into, or computing capability and power into the computing architecture, in the architecture. And this computing power has been extensively growing at the rate of 3 times performance before. If you look at Intel's roadmaps, it has always been 3 times performance vis-a-vis the previous generation processor, or 5 times performance, which came down to 2 times and 1.5 times now. Yeah, so the limitation is, it's going beyond this performance level, would mean that you need to accommodate a lot more transistors, or you need to rely on a completely different architecture model. Yeah, even when you rely on a completely different architecture model, it would still mean that the transistor sizes may need a significant reduction further, which means that the size of the particle, size of the transistor, will hit the subatomic level where the quantum effect um, gets into picture. And in this case, if you look at the traditional semiconductor architecture, it's actually based on switches. Yeah, so it's on or off depending upon the program that you define. And if the quantum effect plays when it moves to subatomic particle, it is expected to behave in that particular manner. This architecture would cease to exist or cease to work in the way that we would like. So, which means that the computation won't be appropriate, or you wouldn't be getting the accurate results, because quantum tunneling would mean that the switch will no longer, switch will no longer be a barrier. Yeah, and the particle or the energy flow would pass through the barrier. So essentially what it means that there is a limitation in terms of how much more progress we can do with the classical computing architecture. And hence there was a lot of investigation, not just into quantum computing, but different types of architecture. So you'll always see now in the supercomputer computing world, ARM processor in addition to Intel processor. Instead of Intel general purpose processor, we're looking into ARM processors, which is a different semiconductor architectures. Again, the supercomputers are capable of providing much higher performance than traditional computers, but that still isn't enough. And we'll see why, and what are these problems that we're trying to solve, which needs that level of computing power. Yeah. So these are some of the investigated areas with these additional problems, which actually urges us to look beyond the classical computing architecture. For example, in financial services, yeah, portfolio risk optimization, or optimization of credit risk and scoring of credit risk, cash replenishment in ATM, workforce scheduling is something which would be applicable across industry. But these are some of the areas which is being investigated in the financial services segment. And the reason being that real-time information, we'll see some of the examples in my upcoming slides. In real-time information is going to make a huge difference for financial services. Yeah, for example, the current economic scenario, if you look at it, or if you actually compare it with the Lehman concern that we saw in 2008, if the portfolio was well distributed with appropriate risk parity and appropriately diversified across various industry, we could have avoided a potential decline of the market. So that is the intent. So what is required there is a real-time assessment of the variance that is seen between the stock prices. And it depends on the parameters one can add, and there is no limit to those parameters. So the minute you add more parameters, you're dealing with a much more complex problems, which is called as a combinatorial optimization problem. If I have to very briefly explain what a combinatorial optimization problem is essentially the sum total of all the possible combination which potentially is required to assess and come to the most optimal solution. Today, all these things are being handled. Yeah, there's no question that financial services portfolio risk optimization is not happening. it's not the most optimal way of working and deriving an answer. And there is a scope, much better scope of improvement. And we'll see how and what difference we can see between these. Similarly, in automotive and manufacturing, I know this is a mechanical engineering division, so we've done small projects in these areas because of the constraints with the current computing system, but we'll get into that. But areas where automotive companies, and this is precisely led by, the demand is led by the large automotive companies like Volkswagen, BMW, Toyota, because they obviously want to drive towards leadership and innovation in this segment and not miss out on any new technology. In automotive segment and manufacturing segment, the areas are immense, yeah, across the manufacturing process, across the job scheduling process, across the every single point in the manufacturing process has an impact if you can apply this computing architecture, including robot welding optimization, which potentially could be for seam sealing. Yeah, potentially could also be activities in paint shop. Paint shop activities are considerably very high, expensive for the automotive provider. This is one of our experience with BMW. And we found that 30 to 50% of the cost is essentially in the paint shop area. Yeah. So any optimization which could be done on these specific areas within the automotive OEM manufacturing segment is of benefit to them, and it saves immense amount of cost. And when we saw the paint shop savings, which could be done with a minimal with one specific robot welding optimization, was in millions a year. So it has a huge impact. Similarly, the pharma materials are creating or identifying new material. Let's just say identifying new material might be a far-fetched thing, but if you look at pharmaceuticals, they spend billions of dollars every year in investigating new drugs. And one of the things they need to do is molecular similarity and discover similar molecules so that you can identify improved drugs. And they spend years and years of research. And the computation capability and computation power would accelerate that research. Yeah, and then you can uh, provide or come up with drugs much easier. So you will see a lot of these projects initiated by IBM, Fujitsu themselves, Microsoft, and D-Wave, which is the only quantum computing, which is the quantum annealing machine, which is available to public as for sales. The rest you can access over the cloud, and you would see a lot of projects, especially during 2020 in COVID, making these servers and making these units accessible to pharmaceuticals, accessible to researchers who's actually investigating in the COVID drug. Yeah, so there is immense potential, and that's precisely why we are discussing this quantum computing, and every company is looking into quantum computing. So the opportunity is immense, and it is applicable pretty much everywhere and every industry. So nothing needs to be spared here. 5G from telco industry keeps investigating about it from a 5G perspective, but they are looking at it from a very basic optimization, which is network rollout. So to identify where you need to deploy all these assets, or appropriate distribution of the assets and appropriate optimization of the network can be done easily and much faster and most optimally, which will be immense cost saving for the telco providers if they apply these solutions. So you'll always find some of the leading companies in each of these segments would be working with technology vendors like us to ensure they're not missing out on anything and they can leverage this capability. So if I'm actually going fast, to just stop me, okay? Because I'm not I haven't met each of you, so I don't know what your individual background is. So I'm just going ahead with what I have. So just stop me in case you have any questions, or if this is something that is very familiar to you. Okay.
Okay, madam. Okay.
Okay.
Yes, ma'am.
Okay. Yeah. Yeah. Sure. Thanks. So just to understand and see how big or how small the problem is. So we spoke about robot optimization. Now, robot optimization can happen in any manufacturing segment, not just the automotive segment. But if we consider an automotive segment, um, this is specifically a problem that we worked with one of the automotive companies, automotive OEM companies, where they wanted to test this for one of their paint shop activities, which is the PVC seam sealing. Yeah, so seam sealing has been existing and was initially done manually, of course, and now it is using robots. Yeah, and it is essentially to prevent air leaks and ensure it is waterproof. And so that's basically in the assembly of the vehicle, car or whatever vehicle, depending upon what design is, has a separate assembly for each design. Yeah, so the sheet metal overlaps in the assembly is checked and ensured there is no there is no issues with respect to air leaks or waterproofs in this process. And apparently, if this, let's say, during the assembly process, if this is not done appropriately, and it moves ahead in the assembly process, the customer was saying that they'd create a new paint shop, and that cost them immensely. So for them, this particular activity was something that they want to test and see if it works appropriately, and if, what is the impact. So when we checked, when you start off with we started initially with 22 seams, and we were dealing with 10 raised to roughly 20 combinations. Now, what is that combination? One thing which is relatable is and often used in quantum computing is traveling salesperson. Though traveling salesperson problem could be solved with normal optimization solutions and does not really require a quantum computing, honestly. So everything is to do with route optimization. This particular problem is to mostly to do with route optimization, but also considering additional parameters. So additional parameters are the areas which makes each of these problems unique. Yeah, and the challenge is to identify those additional parameters and to what extent can the computing architecture actually take it. Yeah, so these are the two things that usually we consider while working with the customer, or the customer or innovation team who wants to investigate this. So for 64 seams, we were dealing with 10 raised to 106 combinations. And to identify optimal, this normal supercomputers would take immense number of time. And if you actually have to put it down, feel like theoretically, if you run it, let's say every single day, then it will be taking millions of years to finish computing and identifying the most optimal solution. Yeah. So what do we do right now is we actually go with the optimal solution you can find today with your traditional computing system. Yeah, which won't be the actual optimal solution, identifying or computing all the 10 raised to 106 combinations. So that's the difference. So the size of the problem, just that you understand. So drug discovery, to do a simple molecular comparison with 50 atoms leads to 10 raised to 48 possibilities. So that is immense amount of time that they're spending to identify which is the and in molecular comparison, the minimal optimal doesn't work really. Yeah, so drug discovery, most of the time you want to identify which is the exact drug that it is similar to. So this is more drug discovery is much more critical than any of the other examples. Yeah, so this the accuracy requirement is much higher. Similarly, the investment portfolio, if you want to find out the most risk averse and high return portfolio across 500 stock and how it should be distributed. And this is not a one-time process. Yeah, portfolio risk analysis, when you're dealing with, let's say, even if it's a mutual fund or banks who are further investing in funds, this is mostly for the investment case is always investigated by banks for for ideally reinvesting the funds that they receive from the customer. So when they reinvest the fund, they want to ensure that it is really risk averse and would not be impacted by any potential economic conditions which is in the future, which may come in the future. And so real time analysis is always helpful for them. But if you're dealing with just 500 stocks, you're dealing with 1.63 into 10 raised to 150 combinations, which needs to be optimally done. So we can't do this today with standard computing. What we do is we have different mean variance methodology or a risk parity methodology with the which the companies use to identify the portfolio distribution. But you will see the difference when you're using a higher end technology in some of the examples when I show a demo in this presentation. Yeah. Similarly, traffic optimization is very, very relatable. So let me quickly move to traffic optimization. So I'm just trying to say that this is, like I mentioned, it's been investigated by the world's leading organization. NatWest is, and in all these organizations, it is the innovation team, of course, which is dealing with it. When it is the IT innovation team. So the challenge for these companies is, of course, budget. I think you would relate to that as well in terms of the universities as well who are investigating. The biggest concern they have is the budget assigned to any new technology, because it's more, it's, let's say, it's nothing which can turn out in 1 or 2 years. In quantum especially, it's years to come. So when you actually think about real time, real benefited, use case solution. So there is many banks, many automotive companies, many in fact, automotive companies also investigating new materials, surprisingly, new materials to actually create battery solutions which is much more optimal, much more healthier to the environment, and so on and so forth. Yeah. So some of these areas are being investigated by them, and most of the demand is led by them. So I think most of you are already aware of what quantum computing does. Quantum computing is where it's a computing architecture. We're trying to leverage the quantum phenomena. So I believe you are aware of these phenomena that we are talking about. Superposition, where we are talking about being in, or it sounds like you're being in all possible states at the same time. Yeah, it can sound absurd. We'll get into the details. Tunneling means that irrespective, so these are waves. Yeah, in quantum phenomena, when you're talking about particles, they don't behave at a single point in time, but it actually behaves like a wave. So tunneling essentially means that if you have a barrier, typically in your classical physics, obviously the particle can't go through the barrier. But when it comes to quantum state, the particle can pass through the barrier, yeah, in the form of a wave. And that is what quantum tunneling is. So essentially, with zero energy dissipation, that's the key aspect. Yeah. So zero energy dissipation, you tunnel through an obstacle without any concerns. Entanglement means acting on a particle here can instantly influence any particle far away. So they are connected. So if a very simple example is, you're sitting in Hyderabad, I'm sitting in Bangalore. So if I'm throwing a dice and it shows 4, and if we are entangled, yeah, if we are entangled, when you throw the dice, it'll also show 4. So you're controlling the activities across multiple areas if with the property of entanglement. And some of these aspects are being leveraged in some computing technology we'll talk about. Very common examples are these, yeah, for these three phenomena, which is very common phenomena which has been discussed about. And the Schrodinger's cat, though talks about being dead and alive at the same time, is not the best example. Yeah, if you know. And the reason being that, I mean, Schrodinger's cat was actually brought in just to make people understand how absurd or how spooky this quantum phenomena is. And the theory, there was immense amount of debate in terms of the fact that a cat can never be dead and alive at the same time. It does not mean that superposition is not real. Instead, what it means is that it is now we know that it is cat is actually big enough and actually interferes with the quantum state. So that is what is called as decoherence. Decoherence is one of the challenges that technologists like us have to ensure that the architecture needs to address this problem. So decoherence happens when quantum behavior is lost into the environment. And decoherence happens when you're actually trying to identify what the solution is as well. But apart from Schrodinger equation, superposition is better understood with wave functions. Yeah, so wave function can have multiple positions. So that's a normal thing. Yeah. Hello. Was there a question? Okay, so wave function has multiple position at the same time when measured, yeah? And when measured, it will be in one place. So that's the point. So in superposition, if you can leverage superposition, it means that you can be at all the places at the same time. So you can compute one problem at the same time. Yeah, so we'll show an example so that you understand it better. So decoherence is one of the challenges which actually, when the decoherence happens is when you actually identify what the answer is. And if it happens too soon, then you probably would not have got an accurate answer. Okay. The other phenomena or the other effect or property that we see in quantum phenomena is energy quantization. Energy quantization is where quantum and quantum mechanics comes from. So waves can only be the particles can only be in certain specific waves. Yeah. So how is energy quantization? So just to explain energy quantization, I'm going a little bit into physics. So the energy field in the proton is in certain bucket shape. Yeah. If I have to, let's say, draw it, or I have another image. One second. Yeah, so energy, if you look at the energy field in the proton, it will be in a similar bucket phase that you see. Yeah, and the neutron will obviously want to get attracted to the proton and want to fall into the pit or the into the pit of the of the proton. So essentially what happens here is, and it's waves, yeah, so it won't ideally fall right at the bottom, but what happens is it will be waves. Yeah? So there are different energy states that you have. Energy quantization is this essentially. So you have they will have a wave over this, you'll have a wave over this, and the motive is to identify what is the global minimum energy level. Because if you can identify what the minimum energy level is, that gives you the most optimal solution for any specific problem. That is energy quantization. Yeah. And what needs to be avoided is that the electron, because it is all, if there is any interference or magnetic field, then you'll see that the electron keeps, moving around in this place, and it's difficult to identify which is the right spot. Yeah. This was just an example. That is energy quantization property. That also significantly applies to the technology capability. Now, just to explain what happens if we are able to leverage, quantum properties. This is one of the simple examples as I was mentioning, traffic optimization. Yeah, and we are referring to 5 pair of location start and endpoints. And if you're dealing with 5 pairs of start and endpoints, and if you want to include all possible parameters, which means that you would want to include all possible units or all possible vehicles which is on that particular route, which potentially could be there, which is bus or a truck or lorry, or I mean any of those vehicles, and potential other parameters which could be considered as also an overlap, which may happen between these vehicles, and what is the essentially to identify the most optimal solution. And we all use Google Map, but it's actually based on the traditional computing system. So when you want to actually identify the most optimal solution, you are dealing with 10 raised to 100 possibilities just with 5 pair of start and ending point. Yeah. And if you have to use the latest supercomputer, which was the K computer, not the ARM-based processor, the K computer takes 10 raised to 86, 84 seconds, which is 13.8 million years. So no, obviously we are not going to be using it that ways to identify the most optimal route in any which ways, but this is an example. Now, if we can actually apply any of the quantum properties or most of the quantum properties, what happens is you can evaluate all these possible. If you're able to leverage, let's say, superposition, you can evaluate all these possibilities at the same time. So in theory, if you can actually manage to be in the quantum state and compute through the and using quantum superposition, it shouldn't take even less than, it should take less than a second to identify what is the most optimal route. Yeah, this is in theory. Similarly, in quantum tunneling, in case of an obstacle while computing, yeah, that obstacle would not take any energy or any additional requirements if you can hold the quantum state to evaluate most of the optimal paths in no time. Similarly, in quantum entanglement. Now, entanglement is a property which is being investigated in the form of quantum internet, essentially for quantum internet, for the communication area, essentially in quantum communication area, because it means that between two locations, like you mentioned, any part of the world, by the way, it doesn't have any restriction from a distance or any other parameter, time or distance perspective. It is about the control, and if the two particles are entangled, then it enables you to secure teleportation. And this is an area which is being invested in cryptography to ensure that it is a very secure path to communicate. And quantum internet may be a possibility if we can theoretically leverage this. Yeah. Any questions? I'm assuming no. Yeah.
No
Hello.
questions, madam. You can
Yeah.
proceed.
Sure. Sure. Okay. So if this was great, now what exactly is stopping us from leveraging or handling this is what I'm going to be covering right now. So quantum computing in general comes with an immense amount of challenge. That is with the very nature of being in quantum state. So there is computing systems that you would find, especially D-Wave, which leverages technology called quantum annealing. You know, and that quantum annealing leverages the property of tunneling. Just keep that in mind. We'll get into the details going forward. So they leverage tunneling, and this is, I mean, it'll be a huge system. So the reason why I've kept a manual to identify how big the system is. Yeah, it's a huge machine which runs in millikelvin scale, which is negative 232, I think 235 degrees centigrade. Yeah, it's negative 230. So it's that cold, and it needs to be significantly isolated because, as I just mentioned, the quantum state can be impacted by any potential disturbance, any potential noise, or any potential magnetic field changes or effect. So it has to be significantly isolated, has to be running in very low temperature, and even so, the stability is a major concern. At this point in time, as of today, we are not able to maintain the quantum state beyond 90 nanoseconds. So within the 90 nanoseconds, you are trying to identify and compute and identify those answers. And what's happening is when you identify those answers, there is a significant accuracy issue. Okay, there is a higher possibility of error, especially as the problem size increases. Yeah, it's more to do with that. Now, if it is only to do with, let's say, you want to solve a 5 atom molecular similarity problem, then you're dealing with much lesser combination. But will a 5 atom molecular similarity problem can actually be used in real life scenario? No. Similarly, the traffic optimization, where we're just talking about 5 pair of start and stop destination, would not be it's not going to be practically useful. You at least need to deploy it across a city. Yeah, and that would lead to a much larger problem. So the issue is with accuracy of the current quantum computing system, because and it's to do with the qubits. Qubit is the quantum bits, is the measurements used in theory. It is 1 qubit. I mean, a qubit is equal to, if n qubit is equal to bit n raised to, yeah, n bits. Yeah, 1 second, sorry. So as qubit, it tend to quickly lose the state of superposition. It possibly provides a lot of error. And there is a mechanism right now in quantum computing to do error corrections. Yeah, error correction does happen, and error corrections methodology is also well defined, but that would not be enough, because firstly it is additional activity which you're conducting, and on top of that, the error correction is not simply sufficient to to solve the problem. Yeah. Yeah, so I got confused. Is 1 qubit is equal to 2 raised to n. N qubit is equal to 2 raised to n bits. Yeah, so one qubit is equal to 2 bits, and 2 qubits will be 4 bits, and it's basically, it depends on that. Now, what is the challenge? So the quantum computing architecture is depending on the physical qubits. So when you hear there is a, let's say, 2000 qubit based system, it means it's 2000 physical qubit based system. Now, the physical qubit does not translate to logical qubit. Yeah. Now, this is a hardware platform that we are talking about. Now, the hardware platform has a software layer over it, which does the computing, and the algorithm needs logical qubits, not the physical qubits. Because if the physical qubit was proportional to the logical qubits, we should have been able to do great things by now with this 2000 qubit D-wave systems. Yeah, but that's not the case. The reason being, what I mentioned is quantum error correction. The reason being that you're essentially on an average burning 100 to 10,000 qubits per logical bit. And that's because of the noise which is created by either magnetic field or temperature changes in the system, or any potential external factors which is impacting the quantum state. As mentioned, we have not been successful in holding the quantum state beyond few nanoseconds. 90 nanosecond was as of last year, and I haven't seen an improvement beyond this, but I'm assuming with much higher qubit systems, the accuracy potentially can also come down. Yeah. So which means that the physical qubits are not universally entangled. If it were universally entangled, we shouldn't have had this problem. So which means that the larger the physical qubits, the better the result should have been. But today, that's not the case. The larger the qubits, it's good, but it's not still translating to the logical qubits. And this disparity between the physical qubits and logical qubits is due to, as I mentioned, all these concerns, and also due to the quality of the qubit, potentially the impurities in the material. So that's why you would always, when you actually research and you identify what Microsoft is doing, you will find that Microsoft is talking about identifying quasi-particle. Yeah. So the particle or the material of the qubit has a big role to play, and there is a significant amount of investigation around that which happens as well. So this is an example I'm trying to say, if like I mentioned, a 5-atom problem would be a much smaller problem size, which needs approximately a 50 logical qubit problem. Yeah, so if you have 50 logical qubits, you should be able to solve this issue. Now, which may require, in the whole logic of burning 100 to 10,000 physical qubits to identify 50 logical qubits, you need 5,000 to 5 million physical qubits to actually solve this problem. There is a 5,000 qubit system, which is the D-Wave system, which was recently released. Actually, it was this year, but it is not really, really exposed yet in the market. But it is possible in their scenario. I think a 5-atom problem could be solved with their 2,000 qubit digital annealing system. But practically, 5-atom is not sufficient for computational chemistry problem. And mind you, this is a computational chemistry problem, not a quantum chemistry problem. Quantum chemistry would be a little more advanced. And I'm not an expert in quantum chemistry, but I do have a colleague and a friend of mine who presented with me in IIT Bombay, who is a scientist and does quantum chemistry. So if you're interested, I can request him to have a session with you. Yeah, but this is quantum chemistry if you're interested in. So the difference between, so I often get this question, so is quantum computer then doing parallel processing? Yeah, which GPU does. Okay, but no. Parallel processing in semiconductor architecture is very different. Parallel processing, as you can see in the screen, this image, when you use GPU, it is one particular problem that you're trying to solve by splitting it into multiple problems. So you're dealing with something where you're actually splitting the task into multiple different problems. It computes separately, adds it up to find the problem, or to find the solution to the problem. But in quantum computer, what you are trying to do is trying to calculate a single problem at the same time at every possible second. Yeah, so it's a different, it is completely different. These two architecture is completely different, and it is not a parallel computer. It is not a parallel computing like a GPU, which happens. It's not high performance computing. Yeah, you in high performance computing, as I mentioned, you are distributing the problem across multiple computing cores and then identifying the solution. But in quantum computing, you actually, it's a single problem which needs to be computed several times, or at the same time, and it's not a split which is happening of the problem. Okay. Okay, so there are different, like I mentioned, there are mainly two types of quantum computer. One is quantum annealing. The other one is quantum gate. Quantum annealing leverages the quantum tunneling property. And today there are 2,000 to 5,000 physical qubit range systems. This is majorly D-Wave system. It's a Canadian-based company, and they provide, I believe they provide cloud access to their systems as well. The systems were being shipped to large companies like Volkswagen, which was extremely expensive in millions. And it's a huge system to manage and maintain. Until last year, they were selling it. Now they have stopped selling the hardware unit, but now they are making it available over the cloud as a service. Yeah. So depending upon your requirement, it's just a basic requirement, then they would probably provide you an access to a 1,000 qubit system or a 2,000 simulated system. The quantum simulation is also done. So it is possible that they create a simulating environment which replicates the same results rather than the actual quantum annealing system over the cloud. The quantum gate system is where significantly a lot of companies, large organizations like Microsoft, IBM, Google, all these companies are working on, a lot of research companies as well. And that's based on a gate architecture, and it's completely different. Quantum annealing is mostly is used for, I'm sorry, I don't know if you can see this, the bottom part. The comparison is that The field of application of quantum annealing is for combinatorial optimization problem. But if you want to solve much more advanced problems like quantum chemistry, want to ensure that internet quantum internet is needs to come into play, so that is a search probability in less than a second, and application in the field of cryptography or cryptanalysis. Quantum gate is the technology that everybody looks to, but the quantum gate technology is not the let's say it's not the mature technology yet. There is a long way to go, and it is less than 100 physical qubits, so you can realize the same challenges that we discussed is there in both. Yeah. And quantum annealing is a little more mature systems already, and it has a much larger qubit range, but of course only restricted to combinatorial optimization problem. So quantum gate could be potentially much more successful in solving much bigger problems if they manage to gain the number of increase the qubit sizes and accuracy rates. Yeah. And it primarily leverages superpositioning and entanglement. Okay, this is just a quote from quantum computing. So when companies like us actually get inquiries from organizations like across the automotive, the concern which they have and we have is the fact of an unknown time scale. Because of the unknown time scale in quantum computing, it becomes very difficult for either of us, like for IT companies, it becomes difficult to invest in that technology, because you need to invest in R&D a lot more to to derive a much more capable system. The problem is the return that we could expect potentially for the next 5 or 6 years would be potentially nil, yeah, almost nil in comparison to the cost. So that's the biggest concern. And the same thing when it comes to the organization. So the organizations like Volkswagen, BMW runs it in their innovation department, and the innovation department obviously is not the business critical department. It is to explore and identify new technology. So they also have very limited funds, especially during 2020 timeframe. You would have heard very little news about quantum computing because of this reason. Yeah. But there was a market basis which we've started there was potentially an increase in discussion since 2018 on this technology, though D-Wave has been in the market since I think 2008 or 2010. Yeah. So the investment, significant investment, is actually happening from the government. Yeah. In the US and Europe majorly, in Japan also significantly. So when we get into some of the examples, I can show what we've done, what some of the things were done in Japan. Okay, so in our case, Fujitsu actually saw an opportunity here, that we saw that this technology is going to take a long time to come. So what is it that we can do today to solve some of these major combinatorial optimization problem? And that is where the technology or the concept of quantum inspired computing came into picture. Okay, so that leverages what is called as annealing methodology. So an algorithm based on annealing metal processing phenomena, which is based on controlling temperature. So annealing process is nothing but, I think you would be very familiar with it, is the Smithy workshop that we do. So you heat the iron, heat the metal, and then keep hitting it till it forms a particular shape. Yeah, so it is the same concept. So when it is at high temperature, this set of unstable atoms, and you will want to shake it so that when you shake it appropriately quickly, and it forms a shape on its own when it cools down. Yeah, the particles come all together to form a specific shape at a lower energy. If we have to theoretically do it, it's a round robin method. Yeah, it's like completing a process. You put the puzzles in together one after the other, may have to go several rounds to do and identify the most optimal most optimal shape or most optimal solution for it. Yeah, so that is, and instead you use leverage annealing method. That's exactly what quantum inspired computing technology is based on. So just to give you a quick update, um, that's the annealing technology. So to the quantum landscape, to the landscape of quantum computer, there actually has been an addition of leveraging this technology in the traditional computer to currently solve some of these problems. Yeah. So that is where companies like Hitachi and Fujitsu is leveraging. Hitachi is using CMOS annealer. We are using enhanced annealing technology. Both are digital circuit annealing methodology. Quantum computers, as I mentioned, quantum annealing and quantum gate. So you have these vendors who are investigating quantum gate computing. Some of them are using a superconductivity itself as a concept for the chip building. It's completely based, like I mentioned, it's based on the particle that you're relying on to find it. In that sense, there are a lot of government initiative and research initiatives around quantum annealing using laser technology and laser network. And in Japan, there is a project called as quantum neural networks. That's a combination, or basically it is to do with leveraging machine learning or leveraging quantum in machine learning or generation of AI neural networks. Okay. Any questions? Are these familiar to you, or is this something new?
Some values are given here. You can write extra write up.
So most of the participants are new to this, so that is why not many questions or no questions, madam.
Okay. So I hope as long as this is useful for you and this is, yeah, you can understand it, it's fine. Yeah. Okay.
We are understanding, madam. Thank you.
Okay. So, like I said, this is the landscape of how the quantum computing infrastructure architecture looks like, which is the hardware side of the play. Now, on the software side, we have something called as a one qubit. One qubit is a company. Okay, in the software side, you need obviously an interface which actually helps in this computation. Yeah, and the computation impact or how quickly the computation happens depends on the underlying technology here, right? But this um, quantum computing algorithm, where it's essentially an engine used to do the computation. It doesn't have a very appealing user interface. Let me just put it directly. So it's basically a set of parameters, an equation created which is called as quadratic unconstrained binary optimization equation. Yeah. So it's a QO engine which points to different solvers right at the bottom, depending upon the solver the customer chose. And it simulates the problem. Okay. Yeah. So one qubit is the most used software vendor and the middleware vendor, what they do is they actually simplify the whole thing by providing a software development kit based on the problem size. So we work very closely. So all the hardware vendors work very closely with software vendors like OneQubit. Mind you, OneQubit is not the only software vendor available. Yeah, but they are the most known and much more advanced software vendor available, because OneQubit and D-Wave jointly work to create this quantum annealing systems back in 2008. So they have that maturity and they have that some of these problems are already defined and developed as a software development kit. But mind you that there needs to be significant work between the software vendor, middleware vendor, as well as the hardware infrastructure vendors to ensure that it works together. And most of the times you will find that the quantum algorithms are common. And over a period of time, the quantum algorithm, this OneQubit has developed their algorithm and the middleware to an extent where you can leverage the quantum algorithm on classical computing systems. When I mean classical computing system is your normal Intel-based servers or Intel-based computing systems. you can still leverage it and find an improvement, yeah, using quantum algorithms. So the what has potentially happened over a period of time, even if the hardware architecture, let's say, the pace at the rate at which it has improved is not been that great to solve current use case problems, the algorithms have matured over a period of time and started providing much more insights than your regular classical algorithms, which is used on classical computers. So you can leverage these quantum algorithms for the specific portfolio optimization problem, or drug discovery or traffic optimization even today. Yeah, and that's just showing a significant improvement. But the constraint is the hardware still needs to support the scale of the problem, depending upon how big the problem size is. So QUBO, as I mentioned, is quadratic unconstrained binary optimization problem. Yeah, it is potentially a pattern comparison methodology. Yeah, identifying the similarities between different parameters defined, and it's a mechanism, or it's a mathematical solution which is used usually in machine learning. Yeah, and that's what is leveraged right now. And it is a it's from a programming perspective, it is very simple. It can be, if the user has a Python based understanding, or C++ or Java, they should be able to handle it. So the interface challenge in the engagement, it is the identification of what exactly should be the equation be, which is the quadratic unconstrained optimization mathematical formula, which maps the problem of that specific customer to this equation. So you need to map that problem appropriately. It would include a lot of trial and testing. So trial and testing to identify the equation. Once the equation is identified, you just feed in the data into the algorithm, and you get back the result. Yeah, it's that's how it works. And then it needs to have an interface to whatever application that you want to drive it. For example, if it is, for example, a traffic optimization activity, then you need to have that layer of application and end user application integrated into this model. So this part of the system only gives you, I mean, not only, it gives you the optimal answer in no time. Yeah, that's the intent. Yeah. So yeah, and as I mentioned, the challenge is to actually create the equation itself, with jointly sit and create the equation itself. But these equations have been defined for very small size problems already. So from a testing perspective, it's easy to do it. And data scientist has the capability of doing QUBO translations. Yeah, so to identify what QUBO works well, and how the QUBO translation should look like, is an area that AI actually does, leverages already for clustering, and hence data scientists are always looked into by all these companies for developing these programs. Yeah, and mathematicians and data scientists are the top two resources that we keep looking for. So quantum inspired computing. Okay, so as I mentioned, quantum inspired is actually traditional computing architecture. Yeah, so it's not the qubit based system, but it's a bit based system which leverages how some of these quantum phenomena functions. Okay, I'll just show you what the architecture looks like so you get it. So for example, these architecture or these mechanism which we have used is on your standard semiconductor classical chip, but the architecture is different. It's not the traditional Intel architecture with which has so many transistor into a single chip. Instead, it is a different model. So inspired by the concept of superposition, we create a unique architecture where what is available today is an 8192 bit model. Okay, then upcoming, and what was released first was a 1024 bit model. Now it is at 8192 bit, which is available. And in the future, what is coming out is a 1 million bit. So the bits, like I said, the problem size, based on the problem size, the number of bits required is much, much higher. So the scale right now is 8,192 bits. So what happens in superpositioning state is that each and every bit processes to identify what energy state is the most optimal state at the same time. Yeah. And so this is the current state. You move to the parallel trial state. So each and every bit tries to compute what is the most optimal state to identify what the problem size is. Now, the because it is not a quantum qubit-based system, it doesn't have the challenges of qubit-based system or quantum computing system, and hence the time taken here, though less, is definitely more than a second. Okay, and hence the accuracy of the result is also much higher. The other area that, like I mentioned earlier, was one of the challenges which potentially could happen was the quantum phenomena, which is quantization that I mentioned, where I was talking about how the electron has a possibility of, falling into this, but it doesn't happen because it is an energy wave. Yeah. Similarly, to avoid this, so because we are relying on the concept of annealing, what has been done is that the state, there is a particular state when the particle actually moves here, we try and escape the low energy state by increasing the temperature of the metal, yeah, or in the chip. So that is basically what happens. And this is coming from quantum tunneling. Basically, as a concept, it is leveraged from quantum tunneling, but this is not real quantum tunneling. Yeah? Just to be very clear, this is a semiconductor system which companies are leveraging so that we get the performance advancement that is required to solve these problems without having the challenges of the true quantum computers. Okay. Similarly, with entanglement, as I mentioned, is to ensure that you're connected across different areas, irrespective of where you are. So based on those concepts, this architecture is put in such a way that all the bits are connected to each other, which provides control and very high precision. So we have a 64-bit precision. Precision is very, very important, which basically means that your solution would be much more optimal than a suboptimal solution. For example, D waves precision, which is only quantum computer which is available, is 4-bit with the 2000 qubit. They claim to have an 8-bit precision with the latest version of 5000. We haven't tested it to understand, but that's the claim. Yeah. So this is a full connectivity system with 64-bit precision. So since you don't have the challenges of quantum computer, this design change in the architecture has helped customers solve these problems. So we'll see some examples. For example, this is the seam sealing automotive vendor solution that I was talking about. So like I mentioned, paint shop contributes to roughly 30 to 50% of manufacturing cost of the automakers. And there are areas in the manufacturing process, if optimized, can reduce significant amount of money and production costs for the company. Just you're actually taking away, let's say, 20 to 30% of the cost of the car, which is significant for the company and the margin. So the example of optimization problem tested and identifying was, like I mentioned, seam sealing. And I think you're aware, or you at least remember what I said. So it's to prevent the air leaks and ensure there is waterproof. And during the sheet metal overlap time in the assembly level, yeah, car assembly level or any vehicle assembly level. And it is a part of the paint shop activity. So we took this example. First was the experimental problem where we had 7 seams being tested. It was tested on digital annealer, which is the quantum inspired technology. And it was tested on D-Wave, which is the true quantum annealing systems that is there. With 7 seams itself, you're dealing with trillions of possibilities. Okay. And with 7 seams, you were able to solve a 7-seam problem, both with the same result, both with D-Wave systems as well as the quantum inspired digital annealer system. But when it went to 22 seams production, the D-Wave system was not able to provide any results. So we have not added it here. The quantum computing today has not been able to provide any results. In fact, the solution result was suboptimal to even 7 seams. So hence, we only tested it with digital annealer, the quantum inspired technology. So with the 1024-bit first generation quantum inspired computing, we were able to handle 22 seams production, and it was production ready, which means that we were providing a optimal solution to optimizing the robot's path to seam seal, which was reducing their expense by 10%. Itself, just 22 seams. But the actual number of seams that would potentially help them is at this level. In fact, it is at 90 seams level. But for 64 seam itself would give them a competitive advantage, would give this automotive vendor a competitive advantage over other vendors because they can bring down the cost of the cars significantly to make a difference. And if it is 90 seams, then it has to be potentially much more bits that needs to be used. I think it has to be roughly about 100,000 bits, which is required to optimize and obtain optimal solution for 90 seams and above. Okay. And this is where customers are investigating and seeing what needs to be done. So as I mentioned, the architecture works on the software development kit from 1 qubit, but it's not restricted to 1 qubit. It can be any software which acts as a solver and does the QBO translation. It's an interface. Yeah. And what you see here is Fujitsu Digital Annealer is what Fujitsu's solution for quantum inspired is. Now, Microsoft also talks about quantum inspired solution, but they don't use any unique architecture. Instead, they use the same quantum algorithms because, as I mentioned, the algorithms have advanced over a period of time significantly that it works better and it can potentially show a difference and better solution when run on a classical computer. So Microsoft, what did they do is they use the 1 qubit software development kits for solving these problems on traditional computing architectures. Yeah. So those are the areas. And yeah, this is a typical process how we engage with these customers. So you first identify the problem. Okay. What the problem is and what parameters. So it's a significant amount of investigation and time which needs to be spent with the right skill sets. Yeah. It usually mostly is data scientists and mathematicians, especially mathematicians would be much more helpful. So it's essentially identifying what all parameters needs to be considered, could impact the problem. What is the problem that you want to solve and how does it help them? Is it a cost impact or if it's a significant impact from a societal perspective, etc. And the challenging part is this: once you identify the problem, mapping that problem to Ising equation or QBO is the biggest challenge. And this is a mathematical model. And this is where we spend most of the time. Once this is finalized, things are very easy with the system, with any system actually, depending upon how good the system is, of course. So in this case, we run it on digital annealer. And as I mentioned, the QBO, essentially what is put into the solver is the QBO. Yeah. Now, we've seen that customers do formulate the combinatorial optimization problem in different models like Ising model, and there are different algorithms to support these QBOs. So if you actually go to 1 qubit site, I would encourage you, if you're interested in quantum algorithms, you can go to 1 qubit site and you will see software development kits for all these algorithms that is defined here. Yeah, graph similarity, K-plex, minimum K-cut partitioning, and graph coloring are very commonly used algorithms, especially for the problems that we defined, which is portfolio optimization, drug discovery, and what else? Drug discovery and robot optimization, traffic route optimization. Quasi-K-click is essentially, I believe it is a Microsoft quasi-particle investigation. This algorithm, we haven't found a use yet for it, but it is available. So if you're interested, I will suggest go to 1QBit site. You will find all these algorithms and what it is used for, the use case of these algorithms, how does it help, and so on. Yeah. So with the quantum inspired computing, we've had successful engagement across all these different industry segments. I'm just quickly going through to give you an example and a demo. So I'll just explain you from a portfolio risk optimization perspective. Yeah. So what we did is, this was an interesting experiment that we did. We actually took the stock prices which actually led to the crash in 2008 and applied different types of methodology that financial industry uses today. Mean variance was what was used during that period. Now, mean variance as a concept, mean variance is used for optimization of costs and distribution of your portfolio. So, if you're someone who's tracking stock market, you know that when you want to invest in stocks, you ensure that the pool of assets are well distributed across multiple industries. And there are definitely different other parameters that financial services or financial industries look into, apart from just industry segments that they belong to, but also, is it a large cap, small cap, and mid cap industry, and how is it actually behaving at a certain particular point in time, and which of these assets are actually behaving similarly across industry at a particular point in time. So these analyses are done on a daily basis, of course, and real time would be definitely a major boost to this. And when we applied what is called as a quantum ready hierarchical risk parity, you could see that it minimizes the risk significantly. So this test actually showed us that you could have avoided a 2008 dip if we had the right methodology, especially for the financial industry to go through. Yeah, banks and so on. When they would like to ensure that the investment is well diversified and risk averse. Yeah. So we were able to maximize the drawdown to 2.5%. That's the risk drawdown that we're talking about. Yeah. And this was the example that we did with NatWest, is one of the companies who's actually invested in 1QBit, and also one of our customers who's working in quantum computing. So I can just quickly show you a demo if you have the time, which shows what the difference looks like. Yeah. That's the, yeah. So risk parity is a methodology which is used today. Yeah, it's just that it doesn't use correlation, and correlation is extremely critical for ensuring that the stock diversification is appropriate. So yeah, this is, one second. Let me just, it went very quickly. So so this is the original covariance metrics. Okay, when you're using your traditional classical computing systems and your and the standard algorithms which is used on classical computing system, and you try to run and solve it, and the quasi-block diagnostication it doesn't show clarity across multiple stocks. What you see at the bottom are just multiple stocks, and if you apply the optimal portfolio based on quantum hierarchical risk parity, you can see how diversified the funds are, and based on the asset ratio or investment in these funds. Now, if you actually look at the mean variance, you will see that there is heavy investment in few funds and no investment at all in much. So it's not well diversified. And mind you, I think this was 50 asset, 50 or 100 asset example. So the more the assets, that is, you pick and choose 500 assets, the covariance metrics becomes even more complex, because you're including that many parameters to compare. Yeah, because you're talking about 500 assets across multiple industry. And it looks a lot more difficult than we can see. So when you use a quantum hierarchical risk parity with the quantum computing, you see how diversified the assets are vis-a-vis the mean variance. Okay, this is an example or a test that we have done with one of the customer datas, and they have started implementing this in their plans. Now the next step that they would like to do is to do this on a real-time basis, okay, which needs potential investment and much higher capacity and computation, and it depends also on the number of assets and parameters that you actually like to compare. The other example which might be interesting for you and can be related to is traffic route optimization. Yeah. So the example taken, as I mentioned earlier, was a 5-pair start and goal point. So by the way, this is a very interesting example because this was done actually for the 2020 Japan Olympics. In 2018, there was a project that the government was looking for to optimize traffic during Japan Olympics. Yeah. And this was one of the areas of investigations which was happening. And we were seeing how digital annealer can optimize this. So while using this in 2018, this was a 1024-bit system. And what we were testing is this 5-pair of start and goal points. So the map shows actually a place in Tokyo. Yeah, and the map in Tokyo, and 5 different locations start and endpoints. So, and there were a number of units for each. This is an example. You basically taking it as an assumption. So we're assuming that the number of units for each route, and it is basically an average number of units that they've identified for that particular route is 20 units, which means that it's a group of vehicles or such a bus or taxi or general car which you might encounter on the way. And the number of candidate routes for each of these pair is 50, each of this unit is 10 routes. So there might be there would be 10 candidate route for each unit. Example. Yeah. So this is an example that we've done, and kind of showing and comparing what it looks like. Okay, 5 start and end goals. So that is we are talking about 1,000 routes, which is 50 routes into 20 units, because we're talking about 10 candidate routes in 5 units. So 1,000 routes, that's one route. This is the second route. So we are basically saying that the number of candidate route combinations which needs to be tested, considering all the parameters or variance that we are expecting with the 10 candidate routes and 5 units across 1,000 routes, is 10 raised to 100 patterns which needs to be computed just with 5 pair of. So just imagine, so if you want to actually get the most optimal path, you need to compute across 10 raised to 100 different combination patterns to identify the most optimal. So if you look at, and that's obviously the reason why we don't use this today, because we don't have access to it as much. When it comes to it needs to be expanded to a city, it cannot just run on 5 routes. So let's just see, we will show you a comparison of how it looks before in the sense what your traditional computing architecture, let's say using Google, how the traffic and how the route recommendation looks like, and how does it look like when it is optimized by digital annealer, which is a quantum inspired. Can you see the difference? Since you were able to compute across the 10 raised to 100 patterns, you were able to identify much better routes to reach the destination with zero traffic. And the time of analysis was 6.677 seconds. Yeah. Now imagine having this backend for your Google Maps. It's a simple example. Yeah, it would be great. Yeah, and this project was actually taken because Tokyo is an extremely high traffic area, but unlike us, the employee, the citizens listen to their government, so they have an app which advises them which is the best route to take that particular day to their office, for example. So that time they might say it is a bus that you need to take, or a train, and not your personal vehicle or your personal vehicle. So it gives options. So they have these apps that is available. and they usually follow those rules. Yeah. And here, so I don't know how effective this thing would be in let's say in countries like India or US, where we do have our own opinion. But this was essentially a project which was done for the Olympics. Now, then we identified that obviously the 1024 is not sufficient. Then we had the 8192, which helps you compute across, let's say, multiple areas within the city, but still not enough. Yeah. So further, the government's plan was essentially to go ahead and mandate people to different routes officially during the Olympic times. Anyways, that's past and Olympics isn't happening now. But this was an interesting project during that period, and I wanted to show you the difference that you would potentially see if quantum computing or quantum inspired computing further advances over a period of time. Yeah. And the total travel time is what we are trying to show for it's not just that the location you identified, and it has also reduced the total travel time for the passengers. Okay. These are some of the examples. So there are more that you see. Some of these companies have already, so like I said, in the financial industry, banking industries have been investigating this significantly. Main Incubator is actually not the typical financial company. It is a banking company, but they have used it in one of their divisions. So they have this division called Main Incubator. The company is actually Commerce Bank. Main Incubator, their role is essentially to investigate and invest in innovative technology. So we have seen that all these large companies have a separate division and separate budget and separate, let's say, KRAs for innovation technology. And Main Incubator from Commerce Bank actually tried and applied it for securitization of the lease agreements for cars. It was a very simple project, but they were able to optimize it significantly. Right now, they've optimized across, let's say, thousands of assets, and they want to cover 10,000 and more assets in that optimization process. These are very small problems. So the problem, you might feel it is a small problem, but it makes significant difference to the customers or the organizations. So the possibilities are immense. It is only the problem is we don't have the time and investment. I think this is a problem with every company that you would see. We don't have the time and investment into further exploring into these areas. So most often, a lot of these projects we drive with universities. There is a collaboration with Canadian University, which is, I'll just take you through that project. It's an interesting one. This is Volkswagen's use case that we did, which is a very simple problem, job shop scheduling, runtime, which was done within less than a second. So now, one thing you should understand is this technology on its own is not going to work. It needs to interact with other technology. For example, in this overall project, we ensured that the optimal solution is obtained in less than a second, and that optimal solution is further used in the rest of the process, supply chain process, using artificial intelligence. So it's a combination of these technologies eventually which will help the end customer. But what quantum computing is promising is real-time information and much faster output to solve a lot of these problems. Yeah. This is one of the projects that we did within the Fujitsu our factory, actually manufacturing factory of the service. So it's a very simple thing which is easy to understand, is basically the inventory management, and part distribution, which was usually done before. They use a tab to identify which part can be obtained from which shelf, and the person will go ahead and go ahead using the tab to identify which part is required in which shelf. So if he's going and getting part 1 from shelf A, and part 3 from shelf C, and part 6 from shelf F, that might be a long route. So what Fujitsu did is that we applied digital annealer Yeah. And when digital annealer was used and optimized, it is optimizing the path that you need to take less time to obtain obtain the parts, obtain the parts through from which shelf, so that you take this is actually a route optimization case. Yeah. So basically you're taking the most optimal route to obtain the part, so that you spend less time identifying and obtaining parts. And most often this part obtaining the part is not usually done manually, it's through robots. So it's mostly to do with how robots are optimizing their parts to obtain these parts and get and supply it to the next location. So there were two optimization done. One is the route optimization. The next level of optimization which was done was shelf positioning optimization. So this is done on a monthly basis. So based on the forecast and the demand, there are certain parts or certain material which is asked for, let's say in the beginning of the year. It's an example. Yeah. And towards the end of the year, it's something else. The shelf location and shelf positions are shifted on a monthly basis based on this analysis to optimize the process within the factory. This is one of the things which was implemented, very simple inventory optimization case. This was also of interest to Toyota in Bangalore office actually. So this will help them optimize their inventory. Now, one of the things which obviously is a must is that you need to have sensors and all that in place in these inventory location to obtain the data. Yeah, that's a basic thing which would be needed to do such analysis. This was the same route optimization was used for fleet optimization in Japan's post office. Yeah, Japan post office. And there we did not use one qubit software. We used an A-star quantum software. They are also a software vendor provider with software development kits, but not as well known as one qubit. This is the same problem that I was talking about, part optimization and picking path optimizations. Yeah, the same traffic optimization case that I just took you through using the demo. Yeah. Showing basically showing the difference, yeah, actual difference when you use the normal same algorithm has been leveraged on a classical computing to derive these paths. If you're using it on a much more advanced technology like quantum or quantum inspired technology, obviously you're not just reducing the travel time but also calculating it much faster. And life science is a very, very interesting area, and it's a very, very complex area. And what we have done so far is molecular similarity. Molecular similarity is an area that we've been able to do well with the digital annealer itself. But when it comes to quantum chemistry, the complications increases quite significantly. But molecular similarity also makes a huge difference in the drug industry. So this is one of the customers who has been using the solution. The other interesting research which I was talking about with the University of Toronto was the radiation therapy. So for cancer radiation therapy, I wasn't really aware of this, but when cancer radiation therapy is done, so for example, if you're affected in a very specific organ, you would ideally like that the laser therapy and only directed to that organ, but most of the time, the way it is analyzed, the therapy mechanism is analyzed, it often damages other vital organs next to it. Yeah. So there's massive number of radiation patterns that the hospital works on, which is a huge number of combination they compute. They take weeks to actually come up with that radiation patterns, yeah, radiation patterns and therapy, which is specific to that patient, with variation of what should be the intensity of the radiation, what should be the direction of that radiation, and different aspects needs to be considered. Now, all these are parameters which needs to be considered, and obviously that will increase the complexity of the problem. So it was a huge computational load which was required to create that treatment plan, the radiation treatment plan, and it simulates taking a lot of time. So when each the beams are from only one direction. Even then, if, for example, if the beams are only in one direction, then you're dealing with a 10 raised to 150 combination. Now imagine if you're dealing with multiple beams, yeah, at different directions. It's going to be immense number of combination which has to be resolved. So this was one of the use cases which we quite, I find it very, very, very appealing, is that this would help in identifying a much more effective radiation plan for each patient, depending upon their diagnosis and the organ that needs to be organ which is based on the organ which is affected. So it will be much more accurate therapy which reduces the risk of side effects, which is significant from a patient's perspective. Yeah? So in case of eradication of one so you can see what has been tested here on the right side. So in case of eradication of 1 centimeter square tumor with precision of 1 millimeter square and 32 intensity levels. So it is 32 different intensity levels from one direction which had to be chosen. So the intensity levels obviously needs to be varied depending upon the therapy and the plan which is defined. So this is what is one of the projects which was done with the University of Toronto. Again, the molecular similarity problem and drug discovery problem being defined. I've almost come to the end of the session and the end of the time that I have. So if you have any questions, let me know, and you can get in touch with me through Dr. Rao also if you have any questions. Yeah. So I'll be happy to address it if I have any knowledge around that, or I can lead you to a person who knows about it. I hope the session was useful, yeah, and I hope you learned something out of this. So
Definitely, ma'am. Session was useful.
okay.
Participants, if you have any questions, you can kindly unmute your mic and ask the question. And even otherwise, if you have any doubts later on, you can forward it to us so that we can contact ma'am for the clarifications and doubts. Ma'am, it seems we are not having any questions. So
Sure.
I would request Dr. Deepak, one of our senior faculty members, for proposing vote of thanks. Deepak, sir.
Yeah, thank you, Mukul sir. So, honorable and respected speaker of the event, Ms. Manju Annie Omen, quantum computing enthusiast and spokesperson, respected head of the department, Dr. P. Srinivas Rao sir, respected principal and the conveners of this program, H. Venkateshwar Reddy and Dr. A. Rajnikant, faculty members of the department, participants, very good afternoon to all. It's my privilege to propose a vote of thanks at this very important talk. So first of all, on behalf of Mechanical Engineering Department as well as the organizing committee of this program, I would like to thank today's eminent speaker, Ms. Manju Annie Oman. It's really a very nice and a good experience to share the knowledge and to know the knowledge about the quantum computing and quantum algorithms. So Madam has made this session very interesting, and within a short span of time, so many topics have been covered, starting from the quantum computing architecture and the quantum properties, leveraging of the quantum properties, and challenges associated with the quantum computing, and as well as a traditional computing architecture, and as well as the examples which have been quoted in the sessions were very, very interesting, and it has made the event as an unforgettable event. So really, those know the traffic, the controlling the algorithm, as well as the example given on this cancer radiation therapy. So a very interesting one. So thanks a lot, madam. Thank you for your accepting for this FDP program, as well as sparing your valuable time out of your busy schedule. I thank you. And at the outset, I would like to thank our principal and the management for continuously encouraging us to organize such programs. I also I also extend my profound gratitude to our head of the department, Dr. P. Srinivas Rao, sir, for getting the idea of organizing a faculty development program on this quantum computing algorithm for CFD. So I also thank the faculty members of the department who are behind the screen and continuously putting their effort to make this program going on smoothly. So finally, I thank all the participants for their patient listening and cooperating with us. Finally, thank you one and all. Thank you, madam. Thank you.
Thank you so much. Those really kind words. And I really hope this was useful for all of you. If you like, I can send across these slides, but I'll have to remove my company logo and some of company specific information. But I don't mind sending you especially the technology part of the slides to you, which should not be a problem. I can send it to Dr. P.C. Rao, sir, and I would be happy to do that. Yeah.
That is your kindness, madam.
We'll be more than happy.
Thank you very much.
Thank you.
So
Thank you for this
participants,
opportunity.
we will be
Thank you.
participants, we will be joining once again at around 2:30 p.m. today. Sir Mukul, sir, any announcement you may please.
Sir, Rao sir was saying something.
Thank you, madam. Thank you. So nice of you.
Thank you. Thank you. Thanks a lot. So can I log off? Because I need to move to my next meeting.
Yes, ma'am. Yeah.
Yeah. Thank you so much. Appreciate it. All of you have a nice day. Bye-bye.
Bye. Yeah, Dr. Mukul, may I request you to announce about the final session, today's final session and its timings, so that the participants will be well aware of the coming up session and closure. Dhanraj?
Yes, sir. Yes, sir.
Yeah, kindly put a word to the participants so that by what time they should be ready.
Okay, sir. Sure. Sir.
Okay, sir. As of now, we will take it as 2:30 p.m. and if any further changes will be informed to you in the WhatsApp. Thank you all.